get started. Finally the audio works, thanks for the technicians. So thanks for coming to the workshop of weekly supervised learning for computer vision. Can everybody hear me in the back? Alright, great. So this workshop is done by Rodrigo, Benenson, Hakan Bilen and myself. I would like to give a special thanks to Vittorio Ferrari, who generally donated slides and gave some pointers. So nowadays computer vision algorithms yield very high accuracy. So already in 2015 it was reported that we achieved about human performance on the ImageNet classification challenge. Also, if you look now at the latest output of the newest detectors, that is mask RCNN, you can see that it's very accurate. So it is very accurate object outlines, and sometimes it even recognizes objects which, if you would look yourself at the image, you wouldn't even notice they were there. So what caused this great advancements? So on one side there's the big advancement of the neural net. So we had first AlexNet, and then it became deeper and deeper until ResNet. On the other hand, we have a large number of images. So we have a large number of training data, and that's one of the big reasons why we can train very accurate classifiers and detectors. But manual annotation is expensive. So if we want to draw a single bounding box for ImageNet, it took about 20 seconds for one bounding box without any quality control. If we want to do segmentation, then a single polygon in the COCO dataset took around 80 seconds one polygon. Annotating a full image for COCO and COCO stuff in total, which you see in the bottom left, took around 19 minutes. And if you go for very accurate annotations, like in cityscapes, it will take about 1.5 hours per image. So that's quite a lot. So, do we need more data? Well, there have been a few interesting studies recently, last ICCP and this year's CVPR, where people trained on millions or even billions of data images as pre-training for classification testing. And what they found in both studies, they found that the return in performance is linear, and it doesn't seem to saturate even if you pre-train on billions of images. So yes, more data is definitely still needed. And for the detection, we have millions of bounding boxes per ImageNet. For open images, it's now 15 million of bounding boxes, but it's still quite a bit far from the billions of images which have been shown to work for pre-training. So we could have more. Also, if you go to semantic segmentation data sets, they're much more expensive to obtain, so there are much fewer images there which are annotated. So, for example, the COCO stuff, which is the biggest, has about 120,000 images, and obviously we can benefit from more data. There's also another flip side of the coin. Instead of just looking at the number of images or boxes, you can also look at the number of categories. So, well, depending on how you measure, there are about 10,000 or 30,000 human categories, and even the biggest data set has only about 3,000 categories annotated, and most of them have actually very few annotations. So making this all manually is very expensive. So one way to overcome this problem is to deal with less supervision. So let's define it more precisely. So in a fully supervised case, the annotation is the same degree as the outputs on the test images. So in the case for object detection, which is the upper part here, we want to have an object detector which outputs bounding boxes. So as training data, we want to have lots of images with bounding boxes. Similarly, for segmentation, we want to have pixel-wise annotations or instance segmentation. So to train models for this in a fully supervised setting, we want to have annotation which has the same degree. So also pixel-wise segmentation or instances. So with supervised learning is learning where we learn from data which is annotated to a lower degree than output in the test images. So the most common case for both object detection and semantic segmentation is to learn from data which is only image level labels. But any annotation degree in between is also a valid form of wiki-supervised learning. So you can also learn from clicks or from scribbles, or for segmentation is also common to learn from bounding boxes. An alternative view of wiki-supervised learning is instead of the goal that you want to train an object detector from wiki-supervised data or train a segmentation model from wiki-supervised data, you can also think of it about as annotating the training data itself. So using the annotations which you have to make the annotation denser so that it is the same degree of the desired output. So Hakan will soon tell about the wiki-supervised learning for bounding boxes, and Rodrigo will do about the wiki-supervised learning for segmentation. One thing, if you have the dual view, where you want to annotate the training data itself, one way to improve this is to put a human in the loop. So if you have a machine which annotates, you can have a human correct the mistakes in order to faster annotate the data. Another way to improve the wiki-supervised learning is knowledge transfer. So we actually have a lot of data where we have quite detailed annotations. So we could use this as a kind of knowledge transfer in order to improve the wiki-supervised learning approaches. So this is the outline for this today's talk. So as I said, first Hakan will talk about wiki-supervised object detection. And then there's a morning break, a coffee break. Then Rodrigo will talk about wiki-supervised learning segmentation. And I will afterwards talk about human-machine collaboration and knowledge transfer. So I will give the spot to
Can you hear me? Okay, well, thanks for coming. So I will start with wiki-supervised object detection. So as Jasper mentioned, we are in an exciting era of computer vision. So in many tasks these days, computer vision algorithms are exceeding human level performance. And there is like new possibilities of having new applications such as autonomous driving and many other exciting ones. So, but to make computer vision algorithms work, we need a person to feed the machine with some annotations or labelings. And so, of course, annotations can be in different detail levels. For instance, you may ask whether to annotate or human, whether there is a motorbike or person in the image. So this is per class. So these numbers can be slightly optimistic. So this may take 1 second per class. Or you may ask more information. You may ask, click on a point on the object instance, and then this may take 2.5 seconds. And you may even ask for bounding boxes. This time it may take more than 10 seconds per instance. And yeah, finally you can ask for pixel labels, and then you can see that as much as, so we ask more details, annotation time, and actually we can maybe change it with dollar signs as well. The cost of annotating is increasing. So, okay, so I will talk about weak supervision as Jasper defined. So we call it, we use a lower degree of annotation at train time than the required output at test time. So this is a bit flexible, of course. So you can also think about it as cheaper one. So in terms of annotation. So what do I mean? So let's assume we have 3 tasks, though we have many more tasks in computer vision. Let's say we want to focus on image classification, object detection, and let's say semantic segmentation. So the source axis is showing what we have in the training time in terms of annotation, and target is showing what we want to achieve, what kind of annotation or output we want to achieve. So this dashed line is showing the regular standard supervision. So it's basically, if you think about it, the middle point is faster RCNN or SST object detector. Maybe the image label one, the first one is ResNet, and the final one can be, yes, some semantic segmentation model like DeepLab. So bottom part, half plane, bottom plane is showing strong supervision if you have more annotations in train time than desired at test time. So what we focus, this tutorial is focusing on the upper side of it. So, so this talk, my talk, will focus on using image level labels in train time, and then getting bounding box predictions in test time. And after me, Rodrigo will talk about using bounding box annotations in train time, and then getting pixel labels in test time. He will also talk about using image label at train time, and then getting again pixel label at the test time. And Jasper's talk is a bit more flexible, so you should think about it as a continuous. There is a continuum between this labeling. So you can obtain also labelings which is let's say annotation time is between getting the image label and bounding box. So okay, so in the standard supervised object detection, we have images, and then training images are provided with their ground truth bounding boxes, per instance. And then we have we can have a SVM, we can have a CNN, something like faster CNN, and then we can use these bounding boxes to measure the quality of object detection and then to train it. So what do we do if we only have an image level label, right? So how do we get the bounding boxes? So this may look magic, but obviously we can say certain things at minimum. So we can say that when image is positive, when there is motorbike, we know that there should be at least one object instance from motorbike category present in the image. And at the same time, we can also say when it is negative. So if we know motorbike class is not present in the image, we can say that there is no object instance from target category in the image. So this is quite obvious. Then, so what kind of principles we can use to get the bounding boxes? So we hope that it is maybe more hope that there exists some set of features that are common to the positive images, and they don't appear in the negative images. And a bit more, maybe, it's a bit more strict one is, so we also hope that, assume that these labels, these features, so when I say features, they might be parts, like if it's a motorbike, it can be a wheel of a motorbike, and which is common in all instances. So then we also hope that these features are lying in the target object instances. So they are somewhere in the box we want to predict. So the first one is going to help us to get the to separate, discriminate positive images and negative images, and second one will help us to localize the object instances. Okay, so let's have a look at the assumptions. So is it so straightforward? So we are looking for common features, and they are common to positives and not common to negatives. So if we think about positive examples, it's not very straightforward to spot some part very similar and exist in all images. Because of intra-class variations, such as appearance, you have a race motorbike, you have a chopper, you have a Vespa. Their scale changes, aspect ratio changes, and then there are occlusions. Sometimes you cannot see parts of the bike, and their view changes. So it's not so easy to find common features. Okay, so let's come into the second one. So we also hope that so there are some common commonalities when we define the object instances. So if you look at these images, so these are coming from Pascal Book 2007, and so this is a person class. So okay, so I'm asking you, who thinks that what is a person? Is it a face, or face plus upper body, or face plus whole body? So who is saying A? Okay, who is saying B? Okay, who is saying C? Okay, so I think many people are doing object detection in Pascal. Okay. So the answer is C. And of course, we have also some images where you can see the whole human. But if you think about it, it's very difficult to tell the weakly supervised object detected person has 2 legs, 2 arms, and a face. So if you look at this, probably it will think, I'm happy with a face, and then all people have face, and some of people don't even have legs in the images, so it should be just face. So this is quite ambiguous. Okay, so the second one is context. So as you see, in this example, all the motorbikes are, there is a person on it, right? Or we can also think that they're always on the road. So how are we going to know what is a motorbike class, right? So motorbike class can be motorbike plus person. It can be person. It can be motorbike plus motorbike, because we have images and we don't really know how many motorbikes exist in this image. So if you always have multiple motorbikes, your weakly supervised object detector may think, okay, maybe 2 motorbikes is a motorbike. Okay, so then a bit more technical challenges. So Jasper explained in a way that we can see weakly supervised object detection or weakly supervised learning as self-annotation. Okay, so for instance, so if you have a supervised algorithm, supervised object detector, you can just fit in the ground truth bounding boxes and then train it for 1 iteration. But in this case, we don't really know where is the person, where is the motorbike. So we have to somehow initialize the bounding box, saying that person is here, motorbike is here. With some heuristics, maybe you choose the whole image. And then you train your object detector, and then iteratively update your belief about where the objects are. So as you see, so for instance, if we have all motorbikes, and then if you put the first bounding box, initialize them on their wheel, probably the object detector will learn motorbike wheel detector. So initialization is very important because of that. And another characteristic problem is overfitting, because we are using very high capacity classifiers, predictors these days. Maybe after the first iteration, your network might perfectly fit into your, overfit into your data, and your bounding box may not move again. But I will go into details more. Okay, so how do we evaluate weakly supervised object detection? Of course, the official way of doing supervised object detection is valid for weakly supervised object detection. So basically, we take the ground truth bounding box, we take our prediction, and then check their overlap, check their union, and then divide them. If the overlap is more than 50%, we are happy. So this is standard Pascal law. But we have something additional, a diagnostic tool as well. So it is from Vito Ferrari's group. And so it's called correct localization. So this is the same thing. The difference is in train time, so you go to the positive training images. So we already know the labels. And we just check, can we still find the ground truth or find a good bounding box overlapping 50% with this bounding box. So the idea here is, if we are able to annotate the training set, if we can recover the original bounding boxes, this means that we can just take a supervised object detector and then use these labels, these predicted bounding boxes, and then we should get the supervised object detection performance. Okay, so let's have a look. So I call it for shades of failure. So we have 4 failure modes. So this is from Jim Bish in Commit 2017. He is using some CNN features and Fisher vectors. So it is showing where it fails. So the first mode is, it is not the failure mode. First mode is correct localization. Second one is when the hypothesis, the predicted bounding box, is covered completely in the ground truth. And second one is hypothesis in the, ground truth in the hypothesis, if the ground truth is covering the whole predicted box, or if our overlap is very low, or if there is no overlap at all. So if it is correct localization, it means we are doing well. So if you look at that, most of the failure cases are in low overlap. So which means we are not doing really good job. We are possibly going to the background. And another interesting observation is categories like person, cat, dog. We always have, in many cases, we have hypothesis and ground truth bounding boxes. This means we are basically detecting the face, and then this face is lying in the ground truth box. And we have also other ones. So we have also ground truth in hypothesis. So if we look at the sheep, boat, and TV, we see that these categories are, in these categories, we have quite a bit context. So typically, object detectors are also picking the context. So for example, if it is sheep, it is taking the grass with it. Or if it is boat, taking the sea with it. Or if it is TV, taking the sofa and the table with it. Okay, so let me ask you, so who has heard about multiple instance learning before? Okay. All right, so multiple instance learning is a general concept. It's not for object detection. It is applied to text categorization, predicting protein binding sites, and so on. So the basic idea is, instead of receiving individually labeled object instances, instead of getting ground truth bounding boxes, we are getting a set of labeled paths. So what do I mean by that? So we are getting a bag of label regions. In this case, those are the red boxes. And so images are bags, windows are the instances, and so what we know is a positive image has at least one positive instance. So if it's a positive motorbike class, we know there is at least one motorbike object instance in the image. If it is a negative image, then we know that motorbike is not in one of the one of the regions here. So our goal is find the true positive instances, and to do that we are going to train a window classifier. So basically, we are going to learn an object detector from just image level labels. Okay. So this is the standard multiple instance learning pipeline. What do? We start with, we generate some windows, so some window candidates or proposal candidates. Hopefully, in one of them, we have our object. And what we do is, we first initialize the right bounding box. We say we talk about our belief. We say that the motorbike lies in this box. Of course, we don't know this. So I'm going to talk about, but a naive strategy is just start with the whole image. And then we take these boxes as ground truth, train our CNN or object detector. Once they are trained, we go to the images again, then we relabel the boxes again. So we check which is the highest scoring bounding box using the trained object detector, and then we do this iteratively. So, okay, so let's talk about, okay, so maybe I should say one more thing. So, obviously, if we do a mistake in the beginning, it might be too late. It might be very difficult to recover the supervised performance. So, because it's an iterative process. Okay, so how do we generate these specs? How do we generate these regions? So one naive way is, of course, if we don't know where the object can be, and if we don't know where to cover, so what we can do is most naively is using a sliding windows. Basically, we go to a data set, maybe we look at a couple of existing annotations, we get a rough idea what are the possible sizes of objects, what are the possible aspect ratios, and then using these things we cover the whole space of translation scales and aspect ratios in this 4D space. But of course, to cover an object, you may need hundreds, thousands of boxes. Although the previous, for example, bag of words can, so if you use a bag of words or an SVM classifier, these things can be done efficiently when you run a sliding window predictor or a detector on it, but with the current SVMs, sorry, with the current CNNs, it's not so obvious. And another very important idea is object proposals. So proposals are a bit different in the spirit that each proposal aims to cover an object. So they are tailored to cover objects actually. So if you have no texture and let's say, for example, sky, it's not going to go and cover the sky. So it's going to focus on some objectness properties, which I'm going to talk about later. So this really made the life easier for weakly supervised object detections. And so most of the recent heavy classifiers can be used with the object proposals. Okay. So let's first talk about initialization. So how do we initialize the right bounding box in the beginning? So a simple strategy is, it is simple, but actually it is effective. So you choose the whole image as the object. And this is safe in a way that you know that this object will be in the image. And some people notice that sometimes this may cause some problems. So if you start with the whole image, maybe your classifier is stuck into the whole image, and then you will not be able to move the boxes, get them smaller. So instead they choose whole image minus a margin. And so there are more sophisticated ways of doing that. So the main idea here is, it is from Song, ICML 2014. So we want to select a subset of candidate windows such that their nearest neighbors of the selected windows correspond to the candidate windows in the positive image. Basically, you take all your training samples, calculate nearest neighbors from across the images, and then you want the samples whose nearest neighbors are only in positive images, not in the negative images. And they should have not only one window, one nearest neighbor, they should have multiple of them. So Song is, they solve it with a discriminative submodel recovery formulation. So in the relocalization, what we do is, so in the standard max margin formulation, the idea is we have an appearance model, so it can be your CNN, it can be your SVM, and B is your proposal, X is the feature coming from that region. So basically this is giving you the probability that how likely the object instance of motorbike is in that box B. So basically what we do in the relocalization is we just take the max scoring window, so most promising window, and this works quite well. And in the case of the training object detectors, so once we self-annotate our data, we can say that the max response should be higher than a margin. So this is an SVM loss, it's a positive margin, and then for the negative images, we still want the maximum scoring window to be lower than some minus margin. This means that all the negative windows should be scoring lower than margin. So you may notice that this is different from the supervised object detection. One problem here is it's not a problem but a limitation. When we use the when we take the max, we just take one positive instance from each positive image, right? But in reality, there might be multiple positive instances. You may have multiple motorbike instances. So this is quite different. And second one is our negatives are coming only from negative images. So we don't really sample from the positive images, negative windows. So if you think about faster RCNN or fast RCNN, these modern object detectors, their negatives are only coming from positive images. So the ones which are overlapping less than a threshold with the ground truth windows. So that's another limitation. So what can we do? So we have all these limitations I talked about before. So one idea is maybe it is not so safe just to choose one bounding box, max scoring one. So to be on the safe side, maybe we can hedge our bets on multiple proposals. So what we can do is we can replace max with a softmax. So this softmax is slightly different than the CNN softmax. We basically take log of sum of exponentials. So it's basically giving a weighted average, sum of weighted average of the proposals, their scores. So what happens in this case is, let's say the top image is showing some object instances and then proposals, some candidates, and max may choose, for instance, in this example, the whole image, or it may group the animals together, cows, for example. But when we have softmax, because it doesn't have to choose a single highest scoring region, it may cover multiple regions. So, but it will give different weights to each of them. So then, training is also similar. So we don't really want the max scoring one to be higher than a margin. We want their weighted average to be higher than the margin. So what else can we do? So this is a non-convex problem. If you start it wrong, it will go wrong. So maybe we should have a more robust optimization scheme. So one idea comes from, inspired from curriculum learning. So the key intuition is, so when we go to school, we start learning with a meaningful order. So we start with easier concepts, we start with calculus, and then move to more and more complex complex calculus maybe later. So self-paced learning, Kumar et al. Here, he suggests that maybe we should start from easier images. Once we are confident, we should add more and more gradually more difficult images. So of course then, for us, easiness is easy. So we can say, if it's a big motorbike, we can say this is an easy image for us to detect. Or if there is not much clutter or occlusion. But for a machine, this is more difficult because we cannot really know the scale of the object without any prior knowledge. So what we do is, so what Kumar is doing is, so he's using an SVM, basically checking the confidence values of the max scoring window, and if they are scoring high, you take that image, and then gradually add more and more difficult ones once the classifier gets more and more complex in a principle. So Another thing, maybe we can use the scale as well. So maybe we shouldn't, in the beginning, go into very small boxes. So we can also just remove the small boxes in the beginning in our image. So they shouldn't go to a very small bounding box. This may also help. There is also newer paper. So it's a bit more sophisticated. So it is basically checking. So in this example, we have only a car. But if your detector thinks that there is a car and a TV, and if TV is scoring higher, so there is some interclass competition. So if interclass competition is working for the wrong class, you don't include that image. When your classifier gets more confident, you include also this sample. Another nice approach is, so the key intuition is here. So it's called multiple instance learning. So when we train object detectors, we are using a set of training images, and then actually we train on them, and then we relocalize on them as well. So think that if your detector is highly capable of overfitting in the beginning, so probably your bounding boxes will never move, right? Because you use the same images to relay the idea. So the idea is quite simple. So maybe we should take the positive images and then split into some random faults, random subsets. And then, for instance, we train an object detector 1 by using image 2 and 3, but we don't use image 1. Similarly, we use image 1 and 3 to train the object detector 2. So these are, all of the detectors have also access to all negative data. So these subsets are only for positives. So finally, we do the same thing. Object detector 3 is taking image 1 and 2. So basically, the object detector 3 never seen image 3, right? So then what we do is we take the object detector 3 to relocalize the positive. So then, so this paper shows that it overfits less to the initial conditions or initial predictions. Okay, so there is also, so we take always the max, but maybe max or soft max, maybe, but these are like not really considering the special neighborhoods, right? So, sorry, that's half. So what this paper is doing, it's self-taught learning is, so we take some, we sample highly confident predictions from an image. I think you may not be able to see, but there are two parrots in this image. And so what we do is we connect the ones which are overlapping more than 50%, and then we take the proposal with most connections. So instead of choosing the max, we take the one with most connections. This means maybe this is the most relevant to the all the samples. And then this is a greedy algorithm. We remove the connected nodes and then iterate again. Okay. So what else can we do? So if we assume that we have n positive images and then each of them have W windows, actually it's quite horrible that if you think about possible configurations is W to the nth power, it's a big space, right? But maybe only one of them is correct. So if you think about supervised object detection, so can we be lazy and eliminate some of the bad ones by using our prior knowledge, which keeps us surviving in this world? So what kind of priors can we use? So we can say that one thing is, so objects should look like each other, right? So we can introduce some pairwise similarity. So for instance here, the sellers in ECCV 2010 proposed a fully connected CRF. Basically, it is taking the max from each image and then connecting all the max scoring windows across positive images. And so this is a unary. I'm going to talk about objectness using objectness as unaries, and then pairwise scores are based on their appearance and also on their aspect ratio. But so this helps and then gives you less overfitting. But the problem is, of course, you can see that the complexity is n square if you have n positive images. And finally, the biggest limitation is not all objects look like each other, right? So even if it's a motorbike, it might be completely different motorbike. So if you look at, for example, this plane images, we have fighter jets, we have jumbo jets, passenger jets, and very different planes. So one idea is maybe we should first cluster them and then check whether it belongs to one of the clusters. So this may kind of handle intra-class variations. But in this case, the problem is you have to choose how many clusters you want, and we don't really know how many, so it may change from class to class. And another idea is maybe we should instead use examples, right? So why do we have to use even clusters? Maybe it doesn't make sense. So what we do here is this Chum and my old paper. So what we do here is we choose a representative from airplane class, and they are chosen from the very confident or discriminating ones. But the problem here is you have to keep all of the examples in the memory, so this can be very memory expensive. Another clue helps us to detect objects is, if we want to take this, its background. For example, if we have a boat in the sea, if we see the sea, and then we can say, okay, there can be a boat there, or like a person on a horse, or a car on the road. So modeling context can help with better separation between foreground and background as well. So there are two ways of introducing background information with the supervised detection. One is additive model. So in the additive, we select a box, and then we use the ring around it as the context information. So this ensures that the predicted object region is compatible with the surrounding context region as well. Or we can also think that an object should really stand out, compared to its background. So in this case, we can use a contrastive model. So Cantero in ECCV 2016 shows that actually these models help to localize objects more accurately. So another very important clue is objectness. So basically, objectness is a measure of the likelihood of the box containing an object, but it doesn't mean that object has to be from certain categories. So it is a generic objectness. So how do we use it? So the advantage of this thing, using this is, so it steers the relocalization towards objects, and then you get away from the background clutter. And also it pushes the detector to have more whole object instead of parts. So how do we use it? It's typically normally we take the max, and instead this time we also put the objectness in our prediction, so we use the score with our predicted score. Okay, so the first objectness came from Alexa in CVPR 2010. So it is using multiple clues such as saliency, contrast, and edge density, and then superpixel straddling. Then this has been further improved by Zipnik and Piotr Dollar. This is called object edge boxes. It's also giving you some measure of objectness. So dollar is, or Zipnik is measuring the number of edges that exist in the box and minus those, the members of the contours that overlap with the box boundary. Basically, the idea is if you have an object, its contours should be in the box. It shouldn't go out of the box. It shouldn't overlap with it. Okay, so there are also simpler things we can do. So using flipped images in data augmentation is very common in these days. So everyone is doing to increase the number of images. But in addition to being extra data, it's also an extra clue for us, right? So, for example, if we mirror an image, the mirror of its output, so when we run our detector on these two images, they should be actually, if we take the output of the mirrored image and then mirror it back, they should be same, right? But it is not, unfortunately. So here you see that these cars are, so red is showing it is confident, blue is showing it's not confident. So this doesn't really work. What can we do is quite simple. We can just minimize the divergence between two heat maps, basically. So it is coming for free without any extra criminal notation. So here you can see that after applying the if you penalize them, the least confident ones are getting a bit more confident. They are turning into orange and yellow from blue. Another thing, it doesn't always hold, but we can also say that a box can tightly cover only one object instance. So this might be not true in some cases, but mostly true. So it's quite variable actually for weakly supervised object detection. And the reason is, for example, if we have, it's quite dark, but we have a TV in the green box and a sofa in the blue box. And actually if we run our detectors, so sofa is below the output of sofa detector and TV is at the top. So you can see that sofa is scoring on the old image. And the reason for that is, so who doesn't have a TV and sofa together in a living room, right? So all of the living rooms have both of them together, so they co-occur. So for weakly supervised object detection, it's very difficult to decorrelate them or spatially separate them. So what we can do is, if we say that they shouldn't be in the same bounding box, and then we analyze such configurations, and then you can see that you can separate them also. Okay, so another thing is scale. So what we can do is we can assume that we should start with bigger images, bigger objects, because they are easier to detect, and then go to the smaller ones because they are more difficult. But how do we know the scale of an object? If we knew it, yeah, it was not weakly supervised, right? So, or at least it wouldn't be weakly supervised in the traditional sense. So what she is doing is going to a small subset of data set. It is learning to actually to output of some size estimates for object instances, and then using them to organize arrange an order of training images. Okay, so another obvious one is motion. So objects, the pixels of objects move together. So we can go to the videos as well, right, to detect them, to detect objects. So Crest is doing that in CVPR 2012. So first of all, to get object proposals, so he's not getting special ones, he's getting tubes instead. So it's using the time as well, using some tracking trajectories. And so once we have this filter tubes, these are noisy, and then we can use objects again to remove some background ones. And this works quite well in videos. But then, if we want to go back to the images, we have a domain adaptation problem, because videos suffer from compression artifacts. They are usually low res. At least it was like that in the past. Maybe today there are more high res videos. So the quality is over. Okay, sorry about that. All right, so if you look at what kind of feature representations we use in weakly supervised detection, is actually it is parallel to the other developments in the computer vision, like to the parallel to the weakly object detection, supervised one. So in the past, we used the SVMs on all these, like Swift bag of words and Fisher vectors, Hawks, and even DPM on Hawks. So more recently, we started to have CNNs, but mostly as black box feature generators, so we didn't really fine-tune them. So then, we have a paper in CVPR 2016, and we said, why don't we fine-tune the CNN? If everyone is doing, we should do it as well. Maybe we were a bit late as well. And then our motivation was clear. So CNNs are, especially pre-trained one, are giving very good results for supervised, so we should also benefit. And then, so some people have evidence that CNNs are learning some objects and object parts, right? So they appear automatically in the image classification. So if this happens, we should also benefit from it, especially in weakly supervised case. But when we apply the standard MRL, at least when I apply it, then I have seen that it just overfits. It starts with the full image and then just learns the full image and then it doesn't move at all. So, and the reason was, of course, these networks are very high capacity. It can really learn quite well at once. Then we thought maybe we should make the problem a bit more difficult. We should split object detection into two subtasks. So what we did was, instead of normally just taking the maximum bounding box for a class, we thought maybe we should, for each image, for each region, we should have a classifier stream. It gives you the class for a region. And then we have a detector stream. It picks the most promising window in an image given a class. So this is not standard MIL because we don't really freeze the parameters, start the CNN with the predicted ones. Maybe this can be called mini-batch, multiple instance time. So if you look at it, so we have an image, and then we have some proposals, they are color-coded. So we take a pre-trained CNN, and then we have two streams. So we get per region, per class, some scores. So classification stream is giving per region a class probability. For example, whether R1 or R2, R3, R4, are they horse or person in this case? And then detection, so if you look at the classification stream, they are normalized over classes. And then detection stream is checking the most prominent or promising region for each class. So they are normalized over regions. So if we take them just element-wise multiply, then you can see that, yeah, in this example, we get quite accurate predictions, probabilities. And then finally, because our ground truth level is only image level, we sum over the all regions and then get the image level prediction and then use this. So the positive sides, this is end-to-end learning, and it really improved the results 2 years ago. It reached 60% of supervised. But, so I was very excited. I have seen with AlexNet it works very well. and then I went to a deeper, more complex network. Then what happened was I was disappointed. So the reason is, what happens there is it learns to focus on very small regions when you use a very complicated or very deep network. And why does it happen? Because if you think about it, my hypothesis is that these deep networks they are very good to find very fine-grained details, right? So because of that, they focus on small regions. Okay, so then some other papers came out. Diba in CVPR 2017. He thought maybe I should better activate the class activations, get bigger regions. So what he does is he's doing some multitask weakly supervised learning. So he's first doing a classification using global average pooling. Instead of using fully connected layers, getting a bigger feature map and then averaging them. So when you do that, you get better, more coverage on the image in the activation maps, and then he uses them to pre-select the bounding boxes, and then he runs a fast RCNN. And then he shows that actually we can go back to similar performance, something like 64% of the supervised counterpoint. So another one is, so we can also, how can we refine them more? So we can take another weakly supervised, my method I shown, and then we can get the highest scoring proposals for positives and negatives. So, sorry, for positives, and then take the overlapping regions with them, and then use them as positives as well. So this, if you look at this images, top ones are showing the early iterations, and then lower ones are the later iterations. Once you start to add more and more overlapping regions as positives, it learns to detect the whole object. Okay, so, and here is some overview of the results. So, the results, you see the percentages are showing basically the relative performance compared to the fully supervised case. So, you can see that it is quite promising in the way that not only the absolute scores of the weakly supervised detection is working, but also we can get closer and closer to supervised. This is quite promising, but we can also at the same time see that there is lots of to do still. Okay, so my conclusions. So this is a challenging task, but fun as well. So, and the reasons are we have lots of intra-class variations, ambiguity with parts context, and optimization is sensitive to initialization, and then it can overfit quite easily. And so we show some solutions like using smart initialization strategies or more robust optimization techniques. And also we show how we can incorporate some prior knowledge. Thank you for your attention. And a small ad before the questions. So I am looking for a good postdoc. So if you are interested to work in these topics, so just come and find me. Yeah, we are going to put it in the web page, and then I guess there is a link to the web page in the CVPR web page as well. Actually, Jasper's talk is only about that. Not only about it, half of the talk is dedicated to human in the loop. So I'm a bit traditional conservative kept on this side. Yeah. Well, I would pick one of the recent ones I have shown, and also, you have to look at the source code, of course, but if you want to know about the techniques, actually, so they built on each other, and so they improve, but at the same time, they get a bit more complex. So it depends where you want to build your model. Yes. Yeah, so if you look at the, actually they should switch actually, those are one. So I think Bilen CVPR18 is with VGG giving 56, with AlexNet it is giving 62 relative improvements, so I should fix that. Yeah. So I just copy-paste them from the papers, but yeah, so I just, for example, I use FastR CNN as the baseline, as the supervised counterpart to get this relative scores.
Hi, so I had a question. Instead of starting from scratch with your weakly supervised models, could you not take an existing highly performing detector like FastR CNN and then use your weakly supervised methods to like push that even further? Like, wouldn't that be more to your advantage than starting from scratch?
Yeah. Well, again, Jasper is going to talk about it as well.
Okay.
So, yeah, but it's a good point. All right. So,
thanks for the nice talk. So as you motivated at the beginning, there are some ambiguities in defining an object class, right? Say a person, you can say the face, upper body, the entire body. So I assume in the weakly supervised setting, that will cause some problem in evaluation. So you can say, if you detect the face, it's correct, but the ground truth is for the entire body. So how could you address this issue in the evaluation?
Yeah, so actually, one of the things happening is using this objective scores, right? So because objective scores are kind of checking whether there is a close contour, let's say if we are using edge boxes or the other one. So these things are happening, but I think there is no certain way of doing it. So I am not sure. Motion is also another way because typically you move together. But otherwise, so I think it's one of the biggest problems. Still, I think most of these methods are focusing on the face of the.
So do you think, say, the same example, if we propose a bounding box for the face, but the ground truth is for the body, so do you think we can somehow change the annotation to leverage, say, like have a group of bounding box for that instance?
Yeah, I mean, typically they're using the supervised evaluation criterion, but so I think it depends on your application. If you are happy to find a face and then so if it's a good enough for you, if you put it in the ground truth or if you define some kind of, so it should be within the ground truth box, that may help.
Yeah. Yeah, thanks.
So we have a coffee break, right? For 15 minutes. So it is. So let's meet at 10:30 again.